Hi there, folks. Welcome to Introduction to Mathematical Ideas, Math 300. This is an introduction to higher mathematics for liberal arts majors. Today, what we're going to do is we're just going to introduce you to the fundamentals of this course so that you are prepared for the semester ahead of you. And so the first thing we want to think about is what is mathematics? And this is a very challenging question. If you get 5 mathematicians in a room, every single one of them is going to have a very different answer for this. But it's something which is good for us to start to think about because that's really the goal of this course. The first thought you might have is the idea of numbers, because whenever we think about mathematics, numbers are usually a big part of it. But then as you start to think about it, you might start to think about geometry. A circle isn't necessarily a number. And so shapes are also included in mathematics. But then there's other things like the idea of logic. Logic would be mathematics, variables, algebra, solving equations, science, measurements, quantities. I mean, all of these things are mathematical objects. If you wanted to, you could even go so far as to say that things like music are included in mathematics as well, certainly mathematical structures. And so the question is, what unifies all of these things and what really is mathematics? Well, one way to think about mathematics is the study of structure. It's an approach to understanding the world around us, similar to how science or theology seek to understand the same questions. The key difference is that mathematics uses a distinct method centered on the idea of developing rigorous definitions and building structures and connections upon those definitions. When we think about it, uh, we define our numbers, and that's one of the earliest definitions we have. We define what 1 is. We define what 2 is in terms of 1. We define what 3 is in terms of 2 and 1. We define what a shape is, what a square is, what a circle is. And then we're able to develop additional theorems based off of those ideas. For instance, when we think about a circle, we might define the number of degrees in it, or we might define it in terms of radians. And then we're able to develop formulas for the area and circumference in terms of those definitions. Often, traditional math curriculum focuses exclusively on algebraic structures with a little geometry thrown in. This course is going to be different. We'll be exploring some of the other structures which are a little more interesting and applicable to all fields. Uh, the math you learn traditionally in school is very one direction. You are just starting with counting numbers and then moving through pre-algebra, algebra, on through trigonometry and pre-calculus and calculus. It's a very linear approach to thinking about math. And there are so many other interesting structures out there. One of my favorites is when we start thinking about the structures of things like sociology. Well, clearly there are mathematical structures there, but what are those structures? Turns out much of it is going to be graph theory and topology, and we'll be exploring some of those this semester. In fact, this semester we've broken it up into 6 modules. And so each one of these modules is going to be introducing different structures or different ways of thinking about problems. If you'd like, here are the 6 modules which we're going to be going over, but let's go through them real quick. And so module 1 is going to be problem solving. And so problem solving, it's a subject which we all inherently understand. When there's a problem, how do we approach solving it? Uh, Oftentimes in mathematics, we focus on the idea of mathematics word problems, which are great and all, but they're not often as real world as we might like. For a real world example, one that I often go to is just the idea of building a birdhouse. And it doesn't really matter what you're building or what you're doing. If you are making something, these are the same types of problems and questions you're going to be dealing with. And so if you want to build a birdhouse, what design do you want to use for it? What materials are you going to need? How much materials? How much is it going to cost? Will you need to make cuts? Are you going to need to have anything to adhere the pieces together? What shapes are you going to need? I mean, there's a lot of questions which go into something as simple as building a birdhouse. Each one of them is a mathematics problem, and each one has a mathematical solution. Uh, we don't have to get precise solutions for each one of them. We can often estimate to get an appropriate answer, but estimation is itself a mathematics tool. And so in this module, Module 1, we're going to explore strategies for solving various numerical problems. Yeah, and it'll be a fun one. The next module is set theory. So set theory is the study of sets of objects, their unions and intersections, and all of the abstractness that can arise. Big picture-wise, sets are just structures which we deal with all the time. Whenever we're classifying an object, we're saying that it belongs to a certain set, but not to others. And these classifications help us better communicate ideas. And so, for instance, if we're talking about an individual, they might have a career, they might have family relationships, they might have friends, they might have hobbies. We can use all of those things to describe the individual. But those descriptors are really saying that they belong to a set or a community. Set theory is just trying to understand these types of communities. Our third module is on logic. And so symbolic logic is an approach to reasoning where we use symbols to denote when something is true or false and build a logical argument based on our understanding of the situation. For example, we know that 3 is an odd number, and all odd numbers are not divisible by 2. Can we say that 3 is divisible by 2? Well, one way to do this is to use true and false statements to try and determine whether or not it is a true or false statement. And we can dissect the ideas of these statements and try to understand facts, opinions, and any declarative statements in as specific a way as we can. This is really the underlying nature of mathematics. We can use rigorous definitions and conditional statements to try to understand the world around us. Module 4 is on numeration systems. So what is a number? Currently, we use a base 10 number system, which is all well and good, but numerical systems and counting dates back to the Ashango bone, which is pictured there. And even animals are capable of basic numeration. There's a great history when it comes to counting systems, as cultures across the world have developed different approaches to numbers, and our approach to counting continues to change in the modern era. It's really interesting to think about math history and how everything's kind of connected. We can actually follow how math and how number systems have changed across the last 10,000 years or so, just by looking at what people have been doing. And it's a very interesting way to explore mathematics. We will have a module based on that idea, and it'll also explore some of the modern approaches to numeration systems. For instance, how does binary or hexadecimal work? We will learn the fundamentals of that. Module 5 is probably going to be the most challenging one because there is a lot to talk about when it comes to probability and counting techniques. When we think about mathematics, mathematics is all about certainty and how we can use rigorous definitions and conditional statements to divine truth. Probability is very closely related. It is a field which uses the tools of mathematics in measuring uncertainty. And so instead of all about certainty, it's about measuring uncertainty. It's not all about counting cards and flipping coins. It's about decision making, though. And so when there are unknowns, probability can ensure you have the highest likelihood of a favorable outcome. I will warn you, there is going to be a lot of difficult computations in this section where you're going to be scratching your head thinking, how do we actually get that? For instance, if we are trying to understand the odds of the lottery, can we figure out what the probability is that we will get 3 out of the 6 numbers in a lottery system? We can, but there's going to be a lot of computations in order to do it. Module 6 is probably my favorite, and it is graph theory and abstract algebra. Graph theory is the study of connection. Whether we are dealing with organizational trees or sports schedules or road systems or human anatomy, the structures in place are generally the same and can be modeled using graphs. These are not like the Cartesian coordinate graphs, which you learn in Algebra 1. Instead, it's kind of like this image here, where we can see a collection of vertices and connections. That's really what graph theory is. It's the study of how objects or individuals are connected to one another. Abstract algebra takes a different approach to the same problems. If we have a set of objects and some operations between them, what properties can we guarantee? With abstract algebra, I often think of the motions of a clock or the motions of a Rubik's Cube. It turns out that the properties when we're talking about those rotations is the same as the properties which we deal with real numbers in pre-algebra and algebra 1. And so being able to take an idea, a set of properties which is familiar, and apply it to a more abstract object is kind of interesting. It also makes it so that you can understand when you experience other operations in the real world. Now let's talk a little bit of logistics, not too much. We'll save that for the syllabus. But in this course, we will be using the homework system ALEKS. For those who have used MyLab or, let's see, one of the other ones, this is going to be a very similar thing, but it's a little bit more tailored to you. And so ALEKS structures the curriculum around you. You're going to begin the semester by doing a knowledge check to see what you currently know. And ALEKS will structure a personalized course focused on the topics you still need support with. There will be videos, there will be textbook support and worked out examples, and it's designed to help you pass the course. From what I've seen, ALEKS is one of the best tools out there for supporting students in mathematics courses. And so we're going to be trying it out this semester, and hopefully it works for you. We will see more about this as it goes on, but my hope is that you will begin working on your ALEKS assignments very, very soon, like in the next day or two. That said, now it's your turn. This course is now beginning, so please do these introductory things. Read the syllabus, which is posted on Canvas, watch the course videos and read your e-text, and begin work on ALEKS. This is a very fast-paced course, and it's easy to fall behind. Make sure that you have put aside enough time to be successful in this course. Do your best to get ahead and stay ahead. That's really the best advice I can give you. If you start to get beat up by some of the homework or whatnot, hit up tutoring as soon as you possibly can, because you do not want to fall behind in this course. The sooner you finish everything, the better off you'll be. That said, good luck, folks. I hope you all have a very good semester. Good luck.